Hello grade 12s and well done for making it to question number 7 of the November 2021 Physical Science Paper 1 exam. Question number 7 deals with electrostatics, which you may recall was taught in grade 10 and 11 and is actually not repeated again in grade 12, even though it will be tested. So it's up to you to go back and to revise all of the grade 10 and 11 content on electrostatics, because there will definitely be a question on electrostatics in your final exams. So displayed to your screen, we have all of the formulae that we use for this section. Firstly, we have a formula that we can use to calculate the electrostatic force. Specifically, this formula allows us to calculate the magnitude of the force. The formula does not provide us with direction. Therefore, when we plug into this formula the charges, we only plug in the magnitudes of the charges, because the plus and minus symbols on the charges do not indicate direction, but rather refer to the nature or the polarity of the charges. Are they negatively charged or are they positively charged? Then we have a formula, actually two formulae, that we can use to calculate the strength of the electric field. You will choose which formula to use based on the information provided. This formula over here relates the potential difference to charge, and we use this formula most especially in grade 10. Then we have the formula at the bottom. This formula is based off of, or is, the principle of quantization of charge. And we know that the N in this formula stands for the number of electrons or even the number of protons in excess on a specific object. Let's now look at question number 7. Question 7.1 says, a small neutral sphere acquires a charge of negative 1,95 times 10 to the negative 6 Coulomb. It's important that whenever you deal with this section on electrostatics, that you ensure that your charges are given in the correct SI unit, and if they're not, that you perform a conversion. Fortunately here, the charge is given in Coulomb. But if it were microcoulomb, millicoulomb, picocoulomb, or nanocoulomb, you would need to convert first, and this is to avoid making unnecessary mistakes in your substitution. This sphere starts off with a neutral, or starts off being neutral, which means that the number of protons and electrons on it are equal to each other. But it then obtains a negative charge. Right? So question number 7.1.1 says, were electrons added to or removed from the sphere? How did the sphere obtain a negative charge? Of course, it is only electrons that can be moved in order to give an object a charge. If we would like to make an object positively charged, we remove electrons. And if we would like to make it negatively charged, we add more negative charges, and therefore we add more electrons. Based on this, the answer to question 7.1.1 is added to, and this is for 1 mark. Question 7.1.2 says, calculate the number of electrons which were added or removed. Now, we are very fortunate in this problem because the sphere started off with a charge, so its initial charge was 0. And in the end, the final charge is negative 1,95 times 10 to the negative 6 Coulomb. So if we're looking to calculate the number of electrons that were added, and we know that they're going to be added because we determined this answer in question 7.1.1, if we would like to determine this number n, then we first need to decide how much charge was transferred. And you may know from what you learned in grade 11 that the charge transferred, if we would like to calculate charge transferred, we sometimes use the symbol change in charge is going to equal to Q final minus Q initial. We plug in these values, negative 1,95 times 10 to the negative 6, and the initial charge is just 0. So in the end, the charge transferred is actually exactly the same as the charge that the object possesses at the end. So the charge that is transferred is this negative 1,95 times 10 to the negative 6. Now that we know how much charge was transferred, we can now go and use this formula, N equals Q divided by QE, where N is the number of electrons and QE is the elementary charge, or we can say it is the charge on an electron. And I would just like to bring your attention to the table of constants that you can find above your formula sheet or above your formulas on your formula sheet. In this table of constants, you're going to find the charge on an electron. So you don't actually need to know the magnitude of the charge on an electron off by heart. So this value, the charge that was transferred, or in other words added to the sphere, is going to equal to negative 1,95 times 10 to the negative 6. We take this value and we're going to divide it by the charge on an electron, which is negative 1,6 times 10 to the power of negative 19. When we put this into our calculators, we find out that the number of electrons that were transferred is 1,22 times 10 to the power of 13 electrons. For a problem like this, you're going to get 1 mark for your formula, 1 mark for substitution, and 1 mark for your final answer. That is going to get you the 3 marks that you can obtain for 7.1.2. Normally, or more often than not, we find that the initial charge on the sphere is not going to be 0. And in those cases, you will also obtain a mark over here, but we don't do so because the charge that was transferred is actually equal to the final charge that the sphere possesses. Question 7.1.3 says, define the term electric field at a point. Very often when we ask learners to define an electric field at a point, they define or state the definition of an electric field in general. But this here is a specific definition. It's an electric field at a point. Therefore, the correct answer to this question is the electrostatic force experienced per unit positive charge placed at that point. This is going to get you the 2 marks that you can obtain for this question. Now, what happened during this paper is that many learners, as normally happens, defined the term electric field in general instead of an electric field at a point. So on your marking guidelines, you're going to see this definition below that 1 mark was awarded for. An electric field is a region of space in which an electric charge experiences a force, and for this only 1 mark was allocated. So please do not lose any marks. Learn the correct definitions off by heart, because electric field at a point cannot be any region of space. It's a specific point in space. Now that we have defined the term electric field at a point, question 7.1.4 says, calculate the magnitude of the electric field at a point 0,5 meters from the center of the charged sphere. So we now have a charged sphere which I'm going to draw. Alright, when you do not have a diagram, it's always very useful to sketch something for yourself that you can better understand the problem. So we have a negatively charged sphere, and at a distance, right, so there is a distance given that is 0,5 meters away from the sphere. It can be towards the left, it can be up, down, it does not matter. It's just a distance that is 0,5 meters away. They would like us to determine the electric field. So what is the electric field experienced over here at 0,5 meters away? At this point, we remember that we have 2 formulae that we can use for electric field. The first one is E equals K, Q divided by R squared. The other formula that you can use is E equals K, sorry, not K, but F over Q. So I'd like to remind you that in this formula, the Q value is the actual sphere or charged object's charge. If we look at the other formula, this one over here, then this Q is the charge of the test charge that we're going to put at a specific point in space away from another charge, and this is the force that that charge is going to experience. If what I have just said confuses you in any way, I'd like to advise you to please go onto the Junior Techie website and watch the videos that have been uploaded on electrostatics in grade 11. So to answer this question, we know for the situation the distance away from the center of the charge sphere where we would like to know the electric field. We also know the charge on the sphere. K is a constant that is always provided to us in our table of constants. You can find this constant over here, so I'm going to highlight it for you. Here's the constant K. This is Coulomb's constant, and it has a magnitude of 9,0 times 10 to the power of 9. So let's plug into this formula all of the values that we know. We know the value of K. We know the charge on the sphere was given to us as 1,95 times 10 to the power of negative 6. Notice that I am not substituting the negative into this formula. That is because this equation determines the magnitude of the electric field. It does not give us direction. In order to determine the direction of the electric field, we need to ask ourselves in which direction will a positive test charge move when it is placed in the electric field. Okay, so please remember, in these formulae, we do not substitute the charge on the charge, so the negative, we only put in the magnitude. The distance must be in meters. Fortunately, it has been provided to us in meters. Please do not forget to square the distance. Many learners, because they're in such a rush and feel so anxious, leave out the square and then they lose their marks. In the end, the final answer that we obtain is 7,02 times 10 to the power of 4 newtons per coulomb. That is the final answer to this question. You're going to get 1 mark for writing down the formula, 1 mark for substituting into the formula, and 1 mark for your final answer. Question 7.2 says, 2 point charges Q1 and Q2 are fixed 0,2 meters apart, and we can see that that is indicated in the sketch. The magnitude of the charges Q1 and Q2 is the same. So we can in a sense say that if this is equal to Q, then that is equal to Q in magnitude. We do not know about the nature of both charges, except that they do say Q1 is negatively charged. So we can go and put a negative in front of that charge. We do not know, so this is not necessarily positively charged. We just do not know at this point. Then they say the small charged sphere with the charge of negative 1,95 times 10 to the negative 6 coulomb is placed at point P. So over here at point P, we have the charge that we dealt with in the previous questions. They say that it is placed 0,03 meters east of charge Q2, and that is indicated in the diagram. The sphere at point P experiences a net electrostatic force of 1,38 newtons towards the west. They've indicated that on the diagram as well in, number form and symbol form. They've also used an arrow to show the direction of this electrostatic force, this net electrostatic force. Now the question reads, calculate the magnitude of the charge on Q2. So, the net force at this point, acting on the sphere, is towards the west. We're dealing with 2 directions, west and east. Let's start off by choosing one of these directions to be positive. I'm going to go and choose towards the east as the positive direction, but you're welcome to choose towards the west as the positive direction. Now that we've chosen this direction, it means that the net electrostatic force, I'm going to include a net there just so that you remember, is going to be equal to negative 1,38 newtons, where the negative sign indicates or refers to the direction. This net force is as a result of the force that Q1 exerts on P and as a result of the force that Q2 exerts on P. So what we're going to do is we're going to write out the force of Q1 on P and the force of Q2 on P, and we're going to try to analyze this as far as possible. When we look at the force of Q1 on P, so we can ignore Q2 for now, we see that Q1 is negatively charged and the sphere at P is also negatively charged. Since both of these charges are negative, we know that this charge, Q1, is going to push the sphere at P away. There are forces of repulsion between the two spheres, and Q1 will push the sphere away towards the east. Based on that, we know that the force that Q1 exerts on P is going to be towards the east, and it is therefore going to be positive. Now, if we look at the force of Q2, we can now ignore Q1. And when we look at the force of Q2, we realize we have a bit of a problem. They did not tell us what type of charge Q2 is. We don't know if it's a positive charge or a negative charge. But we do know that the net force is as a result of only two charges, one of which is towards the east. But this net force is towards the west. The only way in which this net force can be towards the west is if the force that Q2 exerts on it is towards the west. So we now know that this force is going to be towards the west, and it is negative, or in the negative direction. That is how we come to the conclusion. If Q2 is exerting a force towards the west, I think I said left a moment ago, but I meant west, on the sphere at P, then we know Q2 is actually a positive charge. All right, and it is, attracting the sphere at point P. So we can now write out an equation. Remember, net force is the sum of the forces. So we know that the net force at E is going to equal to the force of Q1 on P, which we are taking to be positive because positive here refers to direction, right? So we write down a positive value minus, where the negative refers to direction, F Q2 on P. Okay, this negative, so the fact that this is positive just refers to the direction, and the fact that this over here is negative refers to direction as well. We can now go and expand on this. We know that the net force is negative 1,38. So at this point, we bring into this the direction of the net force. That is going to equal to K. We have the charge of the sphere, which I'm going to just call Q, multiplied by Q1. This is going to be all over R squared. We're making use of Coulomb's law. Minus K, the sphere's charge, multiplied by Q2. All of this over R squared. Where this over here is the distance between Q1 and, the sphere, and this is the distance between Q2 and the sphere. They refer to different distances. If we now plug into this formula a little bit further, we have negative 1,38 is equal to, the K value we know from our table of constants is 9 times 10 to the power of 9. the value of Q was given to us, but when we substitute into the Coulomb's law equation, remember we do not substitute into it negatives and positives for the charges. So we just substitute into this 1,95 times 10 to the negative 6. Q1 I'm going to replace with Q, because Q1 and Q2 are both equal in magnitude, and therefore we can say Q1's magnitude is equal to the magnitude of Q2, and they are therefore both equal to Q. We take this value and we're now going to divide it by the distance between Q1 and the sphere. The distance between Q1 and the sphere is 0,02 plus 0,03, giving us 0,05 meters, and we must remember to square this. We say this plus, again we have the constant 9 times 10 to the power of 9. The charge on the sphere is still 1,95 times 10 to the negative 6. The charge on Q2 is simply going to be Q, and we take all of this and we're going to divide it by the distance between Q2 and the sphere. The distance between Q2 and the sphere is only 0,03 meters. So we plug into the formula now, 0,03 meters, and we do not forget to square it. Our aim now is to solve for Q. So I'm going to show you exactly how we do this. Firstly, using mathematics, we can factorize out the Q so that we get the following. Q, which has been factorized out, multiplied by everything that remains. We have just taken out of this the highest common factor. 1,38 stays on the left hand side. Now to get Q on its own, we're going to divide both sides by this. And when we do so, we find out that Q is going to equal to 1,11 times 10 to the negative 7 Coulomb. That is the charge, the magnitude of the charge on Q1 and Q2, because remember we substituted into the place of Q1 and Q2 the charge Q. They say we need to calculate the magnitude of the charge on Q2, and since they only require magnitude, this brings us to the end of this calculation. So the marks will be awarded as follows. Firstly, you're going to get a mark for writing down that the net force is equal to 1,38 in equation form. You're going to get another mark for writing down Coulomb's law. It is always best to start off by writing it out in its original form, which is K Q1 Q2 divided by R squared, as it appears on your formula sheet, but I have written it out with different symbols so that you don't get confused. Then you're going to get 1 mark for your substitution. Everything that you substituted, I see we've made a mistake, sorry about that. This here should be negative. So this is negative and that's negative. It's the negative over here. Well, not we've made a mistake, I've made a mistake. Sorry, grade 12s. So you're going to get 1 mark for substituting into the formula all of the constants, all of the numbers that we have substituted. But then you're going to get your 2nd mark for taking direction into consideration. Okay, so for this negative sign over there. Lastly, so currently we are on 4 marks. You're going to get your last final mark for finding the value of the charge, which we can now say is therefore Q2. The magnitude of the charge on Q2 is 1,11 times 10 to the negative 7 coulombs, and I would award that, mark over there. So this gives us the 5 marks for this question. And the total for this section on electrostatics is 14 marks. In the next video, we are going to be looking at question number 8. Question number 8 deals with electric circuits. I hope to see you there.